Right now, as you sit there watching this, entire dimensions could be unfolding around you in ways your eyes can't see and your hands can't touch. The universe holds secrets so profound that even our most advanced science can only brush against their edges. What if everything you know about reality is just a fraction of the whole picture? Hidden dimensions, layers of existence beyond our familiar three, might be the key to unlocking the greatest mysteries of the cosmos. From the tightly wound strings of quantum theory to the mind-bending holograms of black holes, scientists have proposed 30 astonishing theories about these unseen realms. Some are grounded in rigorous mathematics, others venture into the wild frontiers of speculation, but all will stretch your understanding of what's possible. This journey will take you from the tiniest folds of space to the vast landscapes of parallel universes, where gravity leaks, time bends, and reality itself might be nothing more than a shadow on a higher dimensional wall. By the time we're done, you'll never look at the night sky or the world around you the same way again. So let's dive in, because the truth is far stranger than anything you've imagined. Now, let's unravel the first mind-bending theory, string theory's hidden dimensions. Picture the universe not as a collection of tiny dots, but as vibrating strings, each note playing a different particle in the cosmic symphony. But here's the catch: these strings don't dance in just 3 dimensions. For the math to work, they need 10 or even 11 dimensions to perform. So where are these extra dimensions hiding? Imagine a garden hose. From far away, it looks like a simple line, one dimension. But up close, you see it's actually a tube with a circular dimension curled up so tightly, it's invisible to the naked eye. That's how string theory explains our reality. 6 or 7 extra dimensions could be compactified, curled up into spaces so tiny, 1 billion times smaller than an atom, that we'd never notice them in everyday life. But why does this matter? Because string theory isn't just about hidden geometry. It's a daring attempt to solve physics' biggest feud. Quantum mechanics rules the tiny world of particles, while general relativity governs the vast cosmos. Yet, these two titans clash violently when forced to work together. String theory whispers a solution. If we embrace these extra dimensions, the equations might finally harmonize, uniting all forces of nature under one elegant framework. That's why physicists, despite the lack of direct evidence, keep returning to this idea. It's a mathematical lighthouse in the fog of cosmic mysteries, hinting that the universe's deepest secrets might be written in dimensions we're only beginning to imagine. And here's the thrilling part: if these extra dimensions exist, they're not just empty backstages. Their shapes and sizes could determine everything from the mass of an electron to the strength of gravity. Change one curled-up dimension's geometry, and you might rewrite the laws of physics itself. So next time you gaze at the stars, remember, the true fabric of reality could be far richer and far stranger than the 3 dimensions your eyes perceive. Now, let's step into another fascinating possibility: the Brane World Scenario. Imagine our entire universe isn't just floating in empty space, but is instead a 3-dimensional membrane, or brane, drifting in a higher dimensional realm. Think of it like a single slice of bread in a cosmic loaf, surrounded by other slices, other branes, each potentially hosting their own universes with different laws of physics. This idea isn't just science fiction. It could solve one of physics' biggest puzzles, the hierarchy problem. Why is gravity so incredibly weak compared to the other fundamental forces? The Brane World theory suggests an answer. Gravity might be leaking into extra dimensions. While electromagnetism and nuclear forces are trapped on our brain, gravity could spread out into the higher dimensional bulk, diluting its strength in our 3-dimensional world. Here's where it gets even more intriguing. If these extra dimensions are large enough, not just tiny curled-up spaces, we might actually detect them. That's where the Large Hadron Collider comes in. By smashing particles at unimaginable speeds, scientists hope to find evidence of gravity's escape into higher dimensions, like tiny ripples in the fabric of reality. If gravity suddenly disappears or behaves oddly in these collisions, it could be a smoking gun for the Brane World Model. So picture this: our universe might be just one sheet in a vast, multidimensional stack with gravity slipping through the cracks. It's a bold idea that reshapes how we see reality, and one that experiments like the Large Hadron Collider are actively probing. Who knows, the next big discovery in physics might come from catching gravity in the act of crossing dimensions. Now, let's rewind the clock to a groundbreaking idea from the early 20th century, the Kaluza-Klein theory. Picture this: in 1921, mathematician Theodore Kaluza made a bold proposal. What if there wasn't just the 4 dimensions we know, 3 of space and 1 of time, but a hidden 5th dimension? Even more astonishing, he showed that by adding this extra dimension, the equations of gravity and electromagnetism could merge into a single, elegant framework. It was as if the universe's 2 most mysterious forces were secretly 2 sides of the same coin. But here's where things get interesting. Physicist Oscar Klein later refined the idea, suggesting this 5th dimension wasn't some vast, sprawling space, but instead curled up into an unimaginably tiny loop, smaller than an atom. Think of it like a garden hose. From far away, it looks like a simple line, but up close, you see it's actually a cylinder. In the same way, our universe might have these hidden, coiled dimensions all around us, too small to notice in everyday life. For a while, this theory captivated physicists. It was one of the first serious attempts to unify the forces of nature. But by the mid-20th century, it fell out of favor. Why? For one, quantum mechanics took center stage, and the math behind Kaluza-Klein didn't quite fit the new discoveries. Plus, without experimental proof, the idea seemed more like a mathematical curiosity than a description of reality. Yet, like many great ideas in science, Kaluza-Klein never truly disappeared. Fast forward to today, and you'll find its fingerprints all over modern physics. String theory, for instance, resurrected the concept of tiny, curled-up dimensions. The idea that extra dimensions could unify forces, that's alive and well in theories aiming to explain everything from dark matter to the birth of the universe. So while Kaluza-Klein might not be the final answer, it planted a seed, one that grew into some of the most ambitious theories in physics today. Who would have thought a 5th dimension, dreamed up a century ago, could still be shaping how we understand the cosmos? Now, let's take a leap into one of the most mind-bending ideas in modern physics, the holographic principle. Imagine if everything you see, touch, and experience in our 3-dimensional world was actually just a projection, like a movie playing on a flat screen. That's the core of this radical theory. Our universe might not be fundamentally 3-dimensional at all, but instead a hologram encoded on a 2-dimensional surface at its boundary. This idea didn't come out of nowhere. It emerged from the study of black holes, those cosmic enigmas where gravity is so intense that not even light can escape. Physicists discovered something strange. The amount of information a black hole can contain isn't proportional to its volume, as you'd expect, but to its surface area. It's as if all the data about what's inside a black hole is somehow stored on its outer edge. This bizarre observation led to the holographic principle, the notion that the universe itself might work the same way. Think of it like a credit card hologram. The flat, shiny surface contains all the information needed to create a 3-dimensional image. In the same way, our universe's entire complexity, every galaxy, star, and even our own thoughts, could be encoded on a distant, 2-dimensional surface we can't see. It's a concept that turns our understanding of reality upside down. After all, if this is true, then the 3-dimensional space we move through every day is just an illusion, a kind of cosmic trick. But why does this matter? For one, it could solve one of physics' biggest puzzles: how to reconcile gravity with quantum mechanics. The holographic principle suggests that gravity in our three-dimensional world might emerge from quantum processes happening on that two-dimensional boundary. It's a bridge between two theories that otherwise refuse to play nice, and here's where it gets even stranger. If the holographic principle is correct, it means the very fabric of space and time isn't fundamental but something that emerges from deeper, more basic laws. It challenges everything we thought we knew about dimensionality, suggesting that the universe is far weirder and more interconnected than we ever imagined. So while the holographic principle might sound like science fiction, it's a serious idea with profound implications. It forces us to ask, what if reality isn't what it seems, and if our three-dimensional world is just a shadow of something deeper? What other mysteries are waiting to be uncovered? Now, let's shift gears to a theory that reimagines the birth of our universe not as a one-time event, but as part of an endless cosmic cycle. Picture this: our universe isn't the result of a single Big Bang, but rather the latest collision between two enormous membranes, or branes, floating in a higher dimensional space. This is the heart of the cyclic model of the universe, a bold idea that turns the traditional Big Bang narrative on its head. Instead of a singular explosion from nothingness, this theory suggests that our universe began when two branes, each representing entire worlds in higher dimensions, smashed into each other. The energy from that collision sparked everything we see today, from galaxies to atoms. But here's the twist: this isn't a one-and-done event. The branes drift apart after the collision, only to be drawn back together by gravity, setting the stage for another cosmic rebirth. It's like a never-ending cosmic heartbeat, with universes expanding, cooling, and then being reborn in a new collision. What makes this model so fascinating is how it sidesteps some of the thorniest problems in cosmology. For instance, the standard Big Bang theory struggles to explain why the universe is so uniform, why temperatures across the cosmos are nearly identical despite vast distances. Inflation theory tries to solve this by proposing a rapid expansion phase, but the cyclic model offers an alternative. The universe wasn't born in a single instant but has been through countless cycles, each one smoothing out irregularities over eons. And here's where extra dimensions come into play. In this model, the branes exist in a space with more than the three dimensions we're familiar with. Gravity, leaking into these higher dimensions, pulls the branes together over unimaginable timescales. When they collide, the energy is funneled into our three-dimensional universe, creating the hot, dense state we call the Big Bang. It's a process that could repeat indefinitely, with no beginning or end, just an eternal dance of creation and renewal. This theory also opens the door to testable predictions. If the cyclic model is correct, future observations might find subtle patterns in the cosmic microwave background, the afterglow of the Big Bang, that differ from those expected by inflation. It's a reminder that even the most abstract ideas about higher dimensions could one day be confirmed or refuted by experiments. So while the cyclic model challenges our intuition about time and beginnings, it offers a breathtaking vision of a universe without end. Whether it's the correct picture or not, it pushes us to think bigger, literally, about the dimensions we can't see and the cycles we might be part of. Now, let's take a closer look at a groundbreaking idea that reshapes how we think about gravity's puzzling weakness: the Randall-Sundrum models. Imagine gravity isn't actually weak, it just seems that way because it's diluted across warped extra dimensions. That's the core of this theory, which proposes our universe is a three-dimensional brane embedded in a higher dimensional space with a dramatic twist, literally. Unlike the flat, compactified dimensions we've seen in other theories, the Randall-Sundrum models introduce a warp factor, a kind of curvature in the extra dimension that amplifies or suppresses forces depending on where you are. Picture this: if our brane sits at one end of this warped dimension, gravity would appear much weaker here because most of its strength is concentrated at the far end. It's like hearing a shout from the other side of a valley. The sound fades as it travels across the distance. This warping isn't just a mathematical trick. It's a potential solution to one of physics' biggest mysteries: why gravity is so much feebler than the other fundamental forces. In this model, gravity isn't inherently weak, it's just spread thin across the warped geometry of higher dimensional space. Electromagnetism and the nuclear forces, meanwhile, are trapped on our brain, making them appear stronger by comparison. What sets this apart from theories with flat extra dimensions is the way it avoids detection. In models where extra dimensions are large but flat, we'd expect to see deviations from Newton's gravity at tiny scales, something experiments haven't found yet. But the warped geometry of Randall-Sundrum models could hide these dimensions so effectively that they'd only reveal themselves in extreme conditions, like near black holes or in particle colliders. The implications are staggering. If this warping exists, it could mean that the true scale of gravity is much stronger than we observe, just masked by the hidden folds of spacetime. Future experiments like precision measurements of gravitational waves or high-energy particle collisions might finally uncover whether this elegant idea holds the key to gravity's secrets. So while the Randall-Sundrum models challenge our intuition about space and dimensions, they offer a compelling way to reconcile gravity's puzzling feebleness, not by changing the laws of physics, but by reshaping the very fabric of reality itself. Now, let's venture into a theory that ties together two of the most intriguing ideas in modern physics: supersymmetry and hidden dimensions. Supersymmetry, often called SUSY for short, proposes that every particle we know has a hidden superpartner with slightly different properties. But here's where it gets even more fascinating. These superpartners might not just be invisible to us because of their nature, but because they're interacting with extra dimensions in ways ordinary matter can't. Think of it like this: if our familiar particles are confined to the three-dimensional brain we call home, their superpartners might have the freedom to move through higher dimensions. This could explain why we haven't detected them yet. They're not just hiding in plain sight, they're slipping into spaces we can't perceive. And this isn't just a wild guess mathematically. Supersymmetry actually becomes more elegant when extra dimensions are part of the picture. One of the most exciting possibilities here is dark matter. What if the mysterious substance making up most of the universe's mass isn't just an exotic particle, but a superpartner that's partially leaking into higher dimensions? This could explain why dark matter barely interacts with ordinary matter. It's not ignoring the rules of physics, it's playing by a different set of rules in a broader cosmic arena. Experiments like the Large Hadron Collider are hunting for signs of these superpartners, and while none have been found yet, the search is far from over. If supersymmetry is real, and if it's linked to extra dimensions, it could solve multiple cosmic puzzles at once, from dark matter to the hierarchy problem in particle physics. So while supersymmetry and extra dimensions might sound like abstract concepts, together they offer a compelling vision of a universe far richer and more interconnected than we've ever imagined. The next time you hear about the hunt for dark matter or new particles, remember, the answer might not just be about what's out there, but where it's hiding. Now, let's turn our attention to a theory that flips everything we know on its head, literally. Imagine a hidden universe identical to ours in every way but one it's mirrored. This is the essence of mirror matter theory, which suggests an entire parallel cosmos exists in extra dimensions, complete with its own particles, forces, and even mirror versions of you and me. Here's how it works. Just as your reflection mimics your movements but remains separate, mirror matter would interact with our world only through gravity. That means while we'd never bump into our mirror twins, their presence could subtly influence the gravitational dance of galaxies. Astronomers have noticed strange gravitational anomalies like galaxies spinning faster than they should, and mirror matter could be the invisible hand behind these cosmic quirks. But why hasn't this shadow universe been detected yet? The answer lies in its symmetry. Mirror particles would behave almost like ghosts, barely interacting with ordinary matter. Some scientists speculate that dark matter itself might be a glimpse of this hidden realm, with mirror neutrons or protons subtly tugging on the fabric of our universe. Of course, not everyone is convinced. Critics argue that mirror matter is an elegant idea without concrete evidence, a cosmic, just-so story. Yet, experiments are underway to test it, like searching for mirror photons or anomalies in neutron behavior. If proven, this theory wouldn't just explain dark matter. It would redefine reality itself, suggesting we're part of a far grander, doubled cosmos. So while mirror matter remains controversial, it's a thrilling reminder that the universe's secrets might not just be hidden in plain sight. They could be lurking in a dimension where everything is flipped, waiting to be discovered. Now, let's shift gears to a puzzle that has stumped physicists for decades: how to reconcile gravity with the quantum world. Quantum gravity in higher dimensions isn't just a tweak to existing theories, it's a complete reimagining of how the universe might work at its most fundamental level. Here's the core challenge: gravity, as described by Einstein's general relativity, operates smoothly across the fabric of space-time, while quantum mechanics deals with discrete, unpredictable particles. These two frameworks refuse to play nice in our familiar 4 dimensions. But what if extra dimensions could bridge the gap? Theories like loop quantum gravity take on new dimensions literally, by proposing that spacetime itself is woven from tiny, interconnected loops. In higher dimensions, these loops could twist and interact in ways that finally unite gravity with quantum behavior. One tantalizing possibility is that extra dimensions might soften the infinities that plague quantum gravity calculations. In our 4D world, predicting how particles interact at unimaginably small scales often leads to nonsensical, infinite results. But in higher dimensions, the mathematics could smooth out these rough edges, offering a clearer path to a unified theory. Some models even suggest that gravity's puzzling weakness in our universe might be a side effect of it spreading out into these additional dimensions. Yet, the road to quantum gravity is far from smooth. Extra dimensions introduce mind-bending complexities, like how to compactify them into shapes that match our observable universe, or why we don't perceive quantum fluctuations in these hidden directions. Experiments to test these ideas are extraordinarily difficult, as the effects would likely appear only at energies far beyond our current reach. Still, the potential rewards are staggering. Success could unlock secrets from the birth of black holes to the first moments of the Big Bang. It might even reveal whether spacetime is truly fundamental or emerges from something deeper. While the math is daunting and the experiments elusive, one thing's certain: if higher dimensions hold the key to quantum gravity, we're standing on the brink of a revolution in physics. So as we grapple with these profound questions, remember the answers might not lie in rewriting the laws of nature, but in uncovering the hidden dimensions where they've been hiding all along. Now, let's venture into one of the most mind-bending ideas yet. What if time itself isn't just a dimension we move through, but something far stranger in higher dimensional space? Time as we know it flows in one direction from past to future, but in extra dimensions, it might behave in ways that defy our everyday experience. Imagine time not as a straight line, but as a landscape where different directions could represent alternate flows or even loops. Some theories suggest that in higher dimensions, time might branch like a river delta, allowing multiple timelines to coexist. This could open the door to theoretical time travel, not by moving along a single timeline, but by navigating between these branching paths. Of course, the physics here is speculative, but the math hints at possibilities that would make even sci-fi writers pause. Then there's the puzzle of the arrow of time. Why does time move forward at all? In our 4-dimensional world, entropy drives this one-way flow, but higher dimensions might offer a deeper explanation. If time in extra dimensions operates without a fixed direction, our perception of a linear timeline could be a shadow of a more complex, multidimensional structure. Some models propose that the Big Bang itself might have locked in our arrow of time from a higher dimensional state where time had no preferred direction. But here's the catch. If time works differently in extra dimensions, why don't we see evidence of it? One answer lies in compactification. The idea that these dimensions are curled up so tightly, their effects on time are microscopic. Another possibility is that we're embedded in a slice of higher dimensional spacetime where time appears linear while the full picture remains hidden. Experiments to test these ideas are still in their infancy, but breakthroughs in quantum gravity or particle physics might one day offer clues. Whether these theories hold up or not, they force us to rethink time's role in the cosmos. Is it a fundamental feature or just a shadow of something deeper? The answers could reshape everything from black hole physics to the origins of the universe itself. And if higher dimensions do rewrite the rules of time, our understanding of reality might be in for a revolution. Next, we'll explore how hidden dimensions could solve one of physics' greatest paradoxes, the mysterious fate of information inside black holes. Now, let's turn our attention to one of the most perplexing puzzles in modern physics, the black hole information paradox. At its core, this paradox challenges our understanding of reality itself. According to quantum mechanics, information can never be truly destroyed, yet black holes seem to erase it completely when they evaporate. So where does the information go? Hidden dimensions might hold the key to solving this cosmic riddle. One groundbreaking idea comes from the holographic principle, which suggests that all the information falling into a black hole isn't lost but encoded on its two-dimensional surface like a cosmic fingerprint. In this view, our three-dimensional universe, and by extension, black holes might be projections from a lower dimensional reality. Extra dimensions could provide the mathematical framework that makes this holographic encoding possible, preserving information in ways we're only beginning to grasp. Then there's the controversial firewall theory, which proposes that black holes aren't as serene as we once thought. Instead of a smooth event horizon, there might be a searing wall of energy that obliterates anything crossing it. This fiery boundary could arise from quantum effects playing out in higher dimensions, where particles become entangled across dimensional boundaries in ways that create extreme violence at the horizon. While this idea remains hotly debated, it shows how extra dimensions could rewrite the rules of black hole physics. But here's the twist: if information isn't lost, how does it escape a black hole? Some theories suggest that higher dimensions allow information to leak out via quantum tunnels or even emerge in entirely separate universes. Others propose that black holes might act as gateways, with information reappearing in unexpected corners of a multidimensional cosmos. These possibilities stretch our imagination, but they also offer hope for reconciling quantum mechanics with gravity. Experiments to test these ideas are still beyond our reach, but future breakthroughs in quantum gravity or observations of black hole mergers might provide clues. Whether through holograms, firewalls, or hidden tunnels, extra dimensions could finally crack the information paradox, and in doing so, reveal a universe far stranger than we ever dreamed. Next, we'll examine how the mysterious force of dark energy might be tied to the hidden fabric of higher dimensions. Now, shifting our gaze to another cosmic enigma, let's unravel the connection between dark energy and the hidden dimensions that might be shaping our universe. Dark energy, the mysterious force driving the accelerated expansion of space, remains one of the biggest unsolved puzzles in cosmology. But what if the answer lies beyond the three dimensions we perceive? Some theories propose that dark energy isn't confined to our familiar spacetime at all. Instead, it could be seeping into our universe from higher dimensions, like water trickling through cracks in a wall. In this scenario, the extra dimensions act as a reservoir of energy, subtly influencing the expansion rate of the cosmos. Alternatively, our universe might be leaking energy into these hidden dimensions, creating the illusion of dark energy as space stretches faster than expected. One compelling model is the quintessence theory, which suggests dark energy is a dynamic field permeating higher dimensional space. Unlike the constant energy of a cosmological constant, quintessence could vary over time and interact with extra dimensions in ways that alter its strength. Another idea comes from Brane World Scenarios, where our universe's expansion is tied to the movement of branes in a higher dimensional bulk. If these branes collide or warp, the energy released could manifest as dark energy in our dimension. But how do we test these mind-bending ideas? Astronomers are scrutinizing the universe's expansion with unprecedented precision, using tools like the James Webb Space Telescope to measure distant supernova and galaxy clusters. Subtle variations in the expansion rate could hint at energy exchange with extra dimensions. Meanwhile, particle accelerators might uncover evidence of higher dimensional fields influencing dark energy's behavior. Whether dark energy is a guest from other dimensions or a sign of our universe's hidden structure, one thing is clear: the answers could redefine reality itself. Next, we'll dive into the intricate shapes of compactified dimensions and how their geometry might hold the blueprint for the universe's deepest secrets. Now, let's zoom in on the hidden architecture of the universe, the intricate shapes of compactified dimensions. Imagine rolling up a piece of paper into a tiny tube. From a distance, it looks like a simple line, but up close, it has a curled-up structure. Extra dimensions might be similarly rolled up so tightly that we don't notice them in everyday life. But here's the twist: their geometry isn't random. The way these dimensions fold and twist could hold the key to everything from particle physics to the very fabric of reality. At the heart of string theory, we encounter Kaluza-Klein manifolds, complex, multi-dimensional shapes that resemble intricate origami at a microscopic scale. These aren't just mathematical curiosities. Their contours determine how strings vibrate, and those vibrations give rise to the particles we observe. A slight change in the shape of a Kaluza-Klein manifold could mean the difference between an electron and a quark, or even the existence of entirely new particles. Then there are orbifolds, simpler, symmetrical shapes that arise when dimensions fold in on themselves like a hall of mirrors. These structures can break symmetries in physics, explaining why some forces appear weaker than others in our three-dimensional world. The geometry of these hidden spaces doesn't just influence particles, it could dictate the very laws of nature. Why does this matter? Because if we could see the shape of these compactified dimensions, we might finally unlock a unified theory of physics. Experiments like those at the Large Hadron Collider are indirectly probing these ideas by hunting for particles that only make sense in higher dimensional frameworks. Meanwhile, mathematicians and physicists collaborate to map out possible shapes, searching for one that matches our universe's quirks. The takeaway: the universe's blueprint might be written in the language of geometry, hidden in dimensions too small to see but too consequential to ignore. Up next, we'll explore an even wilder idea that some extra dimensions might not be tiny at all, but nearly as large as the universe we know. Now, let's stretch our imaginations even further. What if some of these hidden dimensions aren't tiny at all? Picture this: extra dimensions so large they could rival the scale of our observable universe. This isn't science fiction, it's a bold hypothesis that flips traditional string theory on its head. Instead of being compactified to microscopic scales, certain dimensions might extend far beyond what we can see, yet remain invisible to our everyday experience. Here's the puzzle: gravity is shockingly weak compared to other fundamental forces. Drop a paperclip and Earth's entire mass barely pulls it down. But in a universe with large extra dimensions, gravity's feebleness makes perfect sense. The idea is that gravity isn't confined to our three-dimensional space, it spills into these additional dimensions, diluting its strength from our perspective. Imagine a drop of ink spreading through a vast sponge. What seems faint in one small section is actually dispersed across a much larger hidden structure. So why haven't we noticed these colossal dimensions? They could be warped or curved in a way that only gravity interacts with them significantly, while other forces, like electromagnetism, stay trapped in our familiar three-dimensional world. This would explain why particles and light behave as if no extra dimensions exist, while gravity hints at something more. Experiments are hunting for clues. Particle colliders like the Large Hadron Collider might detect microscopic black holes' brief, fleeting signatures of gravity's hidden dimensions, or precision measurements of gravity at tiny scales could reveal deviations from Newton's laws, suggesting unseen dimensional landscapes. The implications are staggering. If large extra dimensions exist, they could rewrite our understanding of cosmic scales, dark matter, and even the birth of the universe. Up next, we'll venture into even more speculative territory where dimensions might not just shape physics, but consciousness itself. Now, let's take a step beyond the purely physical and into the realm where science meets the profound. What if hidden dimensions aren't just about space and gravity, but about consciousness itself? This is where the lines between physics and philosophy blur in fascinating ways. Imagine higher dimensions not as empty mathematical constructs, but as layers of a universal mind, a vast, interconnected awareness that underlies reality. Proponents of this idea argue that consciousness might not emerge from the brain alone, but could be a fundamental feature of the cosmos, woven into the fabric of higher dimensions. Think of it like radio waves invisible to our senses, yet carrying information all around us. If consciousness exists in extra dimensions, it could explain phenomena like intuition, collective creativity, or even reports of mystical experiences where people feel connected to something far greater. Some theorists point to quantum mechanics for clues. The observer effect, where particles behave differently when measured, hints that consciousness might play a role in shaping reality. Could this be a glimpse of higher dimensional awareness interacting with our world? Others cite near-death experiences or meditative states, where individuals describe transcending ordinary space and time as potential evidence of touching these deeper layers. Of course, this theory is controversial. Skeptics argue it strays too far from testable science, while supporters counter that dismissing it outright ignores the mysteries consciousness still holds. Whether you find it inspiring or improbable, the idea challenges us to rethink not just where we are in the universe, but what we are. And that brings us to our next theory, where dimensions might not just shape reality, they could simulate it. Now, shifting our perspective entirely, let's consider a possibility that flips reality on its head. What if the dimensions we perceive aren't fundamental at all, but lines of code in an unfathomably advanced simulation? This is the core of the simulation hypothesis, a theory that suggests our universe might be an artificial construct, like an ultra-realistic video game running on some higher dimensional computer. Philosopher Nick Bostrom laid out a compelling case for this idea. He argued that if civilizations eventually gain the power to create simulations indistinguishable from reality, and if they have any desire to run them, the number of simulated minds would vastly outnumber real ones. Statistically speaking, we're more likely to be living in one of those simulations than in the base reality. So where do extra dimensions fit in? If our universe is a simulation, the rules of physics, including the number of dimensions we experience, could simply be programmed parameters. Just as a video game might render a three-dimensional world while running on a two-dimensional screen, our perceived dimensions could be a simplified interface masking a far more complex underlying code. Some digital physics theories even propose that space-time itself emerges from information processing, like pixels forming an image. This raises wild questions. Could glitches in the simulation reveal hidden dimensions? Might higher dimensional beings be the programmers tweaking the variables? While these ideas stretch the limits of testability, they push us to ponder whether dimensions are absolute truths or adjustable settings in a grand cosmic design. And if that's the case, what does it mean for free will or even the nature of existence itself? As we venture further, remember, whether simulation or not, the next theory suggests dimensions might hold the key to one of quantum mechanics' biggest puzzles. Now, stepping into even more speculative territory, let's explore a theory that blurs the line between science and the unexplained. Could psychic phenomena be evidence of hidden dimensions at work? Some researchers propose that abilities like telepathy, precognition, or remote viewing might not be supernatural at all, but rather a form of perception that taps into higher dimensional spaces beyond our usual three. Imagine if our consciousness isn't confined to the dimensions we perceive. In higher dimensional frameworks, information might travel in ways that defy conventional physics, allowing thoughts or sensations to cross vast distances instantaneously. This could explain why some experiments in parapsychology, like those testing telepathy, sometimes show statistically significant results, even if they remain hotly debated. Of course, the scientific community largely dismisses these ideas due to a lack of reproducible evidence and plausible mechanisms. Critics argue that psychic phenomena often fail under controlled conditions, and many alleged effects can be chalked up to coincidence, bias, or fraud. Yet a small group of researchers continues to investigate, suggesting that if higher dimensions exist, they might provide a physical basis for phenomena that currently seem impossible. Could these elusive dimensions act as a bridge between minds or even across time? It's a tantalizing thought, though one that remains firmly in the realm of speculation. What makes this theory persist isn't just fringe interest, it's the enduring human fascination with the limits of perception and the possibility that reality might be far stranger than it appears. As we peel back another layer of the cosmic mystery, our next theory takes us back to firmer but no less mind-bending scientific ground, where dimensions might hold the secret to the universe's endless variety. Now, shifting our perspective to a cosmic scale, let's dive into one of the most breathtaking ideas in modern physics, the multiverse and its bubble universes. Picture this: what if our entire universe is just one bubble floating in an endless, frothing sea of higher dimensional space, with countless other bubbles, each hosting their own unique version of reality? This isn't science fiction, it's a serious theory called eternal inflation, where the fabric of space-time expands so rapidly that it continuously spawns new universes like bubbles in a boiling pot. Here's how it works. In the early moments after the Big Bang, space may have undergone a phase of exponential expansion, driven by a peculiar form of energy. But instead of stopping everywhere at once, this inflation could have paused in some regions while continuing in others. Where it stopped, a stable universe like ours formed. But in regions where it kept going, new universes bubbled off, each with its own laws of physics, constants, and even dimensions. Some might have more spatial dimensions than ours, others fewer, endless variations in an infinite cosmic landscape. This ties directly into string theory's so-called landscape problem. String theory allows for an astronomical number of possible configurations. Some estimates suggest 10 to the 500 different versions of reality. If our universe is just one of countless bubbles, it would explain why we observe the specific laws and constants we do. We're simply in a bubble where conditions allowed life to arise. It's like winning the cosmic lottery without needing a ticket, but this idea isn't without controversy. Critics argue that if the multiverse can't be tested or observed, is it even science? Supporters counter that certain signatures in the cosmic microwave background or gravitational waves might one day reveal collisions between neighboring bubble universes. Until then, the multiverse remains a dazzling possibility, one that challenges us to rethink not just our place in reality, but the very nature of reality itself. As we ponder the implications of infinite universes, our next theory brings us back to something equally mysterious but far closer to home. quantum entanglement and how hidden dimensions might explain its spooky connections. Now, let's zoom in from the vast multiverse to something far smaller but just as puzzling: quantum entanglement, that eerie connection between particles that Einstein famously called spooky action at a distance. What if this strange phenomenon isn't spooky at all, but simply a hint of hidden dimensions at work? Imagine two entangled particles instantaneously influencing each other no matter how far apart they are. In our three-dimensional world, this seems impossible, but what if they're secretly linked through a higher dimensional shortcut? Here's the idea. In string theory, extra dimensions aren't just curled up, they could create bridges between points in our familiar space. Picture two ants on opposite sides of a piece of paper. To them, the distance seems vast, but if the paper bends in a third dimension, they could touch by moving through the fold. Similarly, entangled particles might communicate through hidden dimensions, making their connection local in a higher dimensional framework. This could explain why changes to one particle instantly affect its partner without breaking the cosmic speed limit set by light. This theory offers a way out of quantum non-locality's biggest headache. How can particles know what happens to each other faster than light? If their interaction happens through extra dimensions, it's not magic, just physics we haven't fully mapped yet. Some models even suggest that gravity, the weakest of forces, might leak into these dimensions, subtly influencing entanglement in ways we're only beginning to explore. Of course, not everyone's convinced. Critics argue that hidden dimensions are still speculative, and entanglement might just be a fundamental feature of quantum mechanics, no extra dimensions needed. But supporters point to experiments where entangled particles behave in ways that defy classical explanations, leaving the door open for radical ideas. Whether or not hidden dimensions are the answer, entanglement remains one of quantum physics' deepest mysteries, and a tantalizing clue that our universe might be far more interconnected than we ever imagined. As we unravel the threads of quantum weirdness, our next theory takes us into even stranger territory: the idea that advanced extraterrestrials might not just be out there in space, but lurking in dimensions beyond our perception. Now, shifting our perspective from the quantum realm to the cosmic unknown, let's explore a theory that blurs the line between science fiction and cutting-edge physics: the idea that advanced extraterrestrials might not just exist in distant galaxies, but in dimensions beyond our own. Imagine civilizations so advanced they've mastered the fabric of reality itself, navigating hidden dimensions the way we navigate roads or oceans. This isn't just wild speculation. Some researchers argue it could explain baffling UFO phenomena that defy conventional physics. Take reports of crafts appearing and vanishing instantly, or moving at impossible speeds without sonic booms. In our three-dimensional world, these feats break the laws of physics. But if these objects are slipping into higher dimensions, they could bypass our spatial constraints entirely. Think of it like a two-dimensional creature watching a three-dimensional object magically disappear by moving up out of its plane. To us, a higher dimensional craft might seem to defy logic, but only because we're trapped in a limited view of reality. Some scientists, like astrophysicist Jack Vallée, suggest that UFOs could be probes or observers from these hidden dimensions, studying us the way we study microbes under a microscope. Even the U.S. government's recent UFO investigations have acknowledged encounters with objects exhibiting transmedium capabilities, moving seamlessly between air, water, and space, as if unbound by our dimensional rules. Could this hint at technology leveraging extra dimensions? Of course, skepticism is healthy. Mainstream science demands evidence, and so far, no smoking gun links UFOs to higher dimensions. Critics argue that unusual aerial phenomena often have mundane explanations, from atmospheric effects to classified military tech. But proponents counter that dismissing the idea outright ignores the deeper question: If extra dimensions exist, wouldn't advanced beings, whether extraterrestrial or beyond our current understanding, find ways to exploit them? The alien dimensions hypothesis forces us to confront how little we truly know about the universe's architecture. Whether these theories hold water or not, they expand our imagination, reminding us that reality might be far stranger and more interconnected than we've dared to dream. And speaking of life in unexpected places, our next theory asks an even wilder question. What if biology itself could evolve to harness extra dimensions? Now, let's take this idea in a thrilling new direction. What if life itself could evolve to harness extra dimensions? Picture organisms not bound by our familiar three-dimensional space, but capable of growing, moving, and interacting in ways that seem impossible to us. This isn't just science fiction. Mathematicians and biologists have actually modeled how life might adapt in higher dimensional environments, and the results are mind-bending. Think of a simple creature in a two-dimensional world like a flatworm on a sheet of paper. It can only move forward, backward, left, or right. But if that worm could access a third dimension, it could suddenly lift off the page, escaping predators or reaching food in ways its flat neighbors couldn't. Now scale that up. What if four-dimensional lifeforms existed? They could appear or disappear from our view, pass through solid objects, or even have body structures we can't fully perceive, like organs that extend into unseen directions. Some researchers have used mathematical models to explore how evolution might play out in higher dimensions. For example, in four-dimensional space, the surface area of an organism relative to its volume changes dramatically, affecting how it absorbs nutrients or regulates heat. Predators might ambush prey from angles we can't conceive of, and plants could grow in shapes that seem to twist impossibly in our three-dimensional slice of reality. There's even speculation that certain complex biological structures, like the folding patterns of proteins or the neural networks of brains, might hint at hidden dimensional influences, though this remains highly speculative. Of course, we have no proof that such life exists, but the mere possibility forces us to reconsider what life could look like in the universe's full-dimensional tapestry. If organisms can exploit extra dimensions, evolution might have produced forms of biology far stranger than anything on Earth. And that leads us to an even deeper question. Could higher dimensions hold the key to consciousness itself? Now, shifting our perspective from biology to belief, let's explore how humanity's spiritual traditions have long grappled with the idea of hidden dimensions centuries before modern physics even existed. Across cultures and religions, the concept of higher planes of existence isn't just a fringe idea. It's woven into the very fabric of sacred texts and mystical experiences. Take Hinduism's ancient Vedas, for example, which describe multiple lokas or realms stacked like layers of reality. These aren't just metaphorical, they're detailed cosmologies where beings exist in states beyond our physical perception. Similarly, Buddhist teachings speak of 31 planes of existence, with higher dimensions reserved for enlightened beings who have transcended ordinary space and time. Even Abrahamic traditions hint at this. Think of Jacob's ladder in the Bible, bridging earth and heaven, or Islamic descriptions of the seven heavens, each with its own vibrational frequency. What's fascinating is how these age-old ideas eerily parallel cutting-edge physics. The Hindu concept of the unmanifest Brahman, a dimensionless reality from which all dimensions emerge, sounds strikingly similar to modern theories proposing that dimensions themselves are emergent phenomena. Mystics who speak of ascending to higher spiritual planes might be describing, in poetic terms, what physicists now model as compactified or warped extra dimensions. Of course, science and spirituality aren't the same. One relies on empirical evidence, the other on revelation and experience, but the overlap invites profound questions. Could ancient seers have glimpsed deeper truths about reality's structure through meditation or visionary states? Or is this convergence simply humanity's universal tendency to explain the unknown through layered realities? Either way, it suggests that our quest to understand hidden dimensions isn't just a scientific endeavor, it's a deeply human one, spanning laboratories and temples alike. This interplay between the sacred and the scientific leads us naturally to another frontier where mathematics itself becomes the ultimate language of reality. Now, let's take a step into a realm where mathematics isn't just a tool for understanding the universe, it is the universe. This brings us to Max Tegmark's mathematical universe hypothesis, one of the most radical ideas in modern physics. Tegmark proposes that reality isn't just described by math, it's fundamentally made of math. In this view, every dimension, every particle, even consciousness itself, is just a mathematical structure. Think of it like this: the universe isn't running on math like a computer running code, it is the code. Tegmark argues that all possible mathematical structures exist as physical realities, and our universe is simply one of them. Those hidden dimensions we've been exploring, they're not just curled up spaces or branes, they're abstract equations manifesting as geometry. This extreme form of Platonism suggests that math isn't invented by humans but discovered, like uncovering the blueprints of existence. What's mind-blowing is how this idea flips traditional physics on its head. Instead of asking why the laws of physics are mathematical, Tegmark says they have to be, because reality is math. Even the apparent randomness of quantum mechanics could just be our limited perspective on a deeper, deterministic mathematical layer. Critics argue this is untestable metaphysics, but supporters point to eerie coincidences, like how pure math often predicts physical phenomena decades before experiments confirm them. Whether you find this hypothesis exhilarating or unsettling, it forces us to confront a profound question. If the universe is just a giant math problem, what does that make us? Are we self-aware equations, or is consciousness itself a mathematical pattern? As we ponder that, let's turn to an even more intimate connection between dimensions and the mind. Now, let's venture into one of the most intriguing intersections of science and philosophy, the idea that consciousness itself might be woven into the fabric of higher dimensions. This isn't just about brains producing thoughts, it's about the possibility that awareness is a fundamental feature of reality, existing beyond the three dimensions we perceive. Imagine consciousness not as something confined to our skulls, but as a field or dimension that permeates the universe. Some theories suggest that what we call mind could be a higher dimensional phenomenon, interacting with our three-dimensional world in ways we're only beginning to grasp. This aligns with integrated information theory, which proposes that consciousness arises from the complexity of information processing, whether in a brain or, hypothetically, in the structure of space-time itself. Then there's panpsychism, the view that consciousness is a universal property of matter. In this framework, even particles might possess a rudimentary form of awareness. Combine this with extra dimensions and you get a startling picture. What if these hidden dimensions are where the stuff of consciousness resides? It's a radical idea, but one that could explain why subjective experience feels so irreducible, because it's tapping into a deeper layer of reality. Critics argue this veers into metaphysics, but proponents point to puzzling phenomena like quantum entanglement, where particles seem aware of each other's states instantaneously. Could this be a glimpse of consciousness operating in higher dimensions? Whether you find this compelling or speculative, it forces us to rethink not just the universe but our place within it. If consciousness is dimensional, then every thought might be a ripple in the geometry of existence. With that in mind, let's turn to another cutting-edge concept: time crystals, and how they might dance through these hidden dimensions. Now, shifting our focus to something truly groundbreaking, let's explore the mind-bending world of time crystals. These aren't science fiction, they're real, and they might hold the key to understanding how hidden dimensions shape the fabric of reality. Time crystals are a bizarre new phase of matter that defies conventional physics. Unlike ordinary crystals which repeat their atomic patterns in space, time crystals repeat their patterns in time. Imagine a structure that oscillates endlessly without any energy input, like a clock that ticks forever without winding. This strange behavior was first proposed in 2012 by Nobel laureate Frank Wilczek, and by 2017, scientists had actually created them in labs using quantum systems like chains of ions or diamond defects. But here's where it gets even wilder. Some physicists speculate that time crystals could be manifestations of higher dimensional physics. If extra dimensions exist, their geometry might influence how these crystals oscillate, creating patterns we can't fully explain with our three-dimensional models. Think of it like a shadow on a wall. What we see in our dimension might just be a glimpse of a more complex dance happening in unseen dimensions. Recent experiments have only deepened the mystery. Researchers have observed time crystals interacting in ways that suggest non-local connections, almost as if they're talking through hidden dimensions. This could revolutionize our understanding of quantum mechanics, dark matter, or even the nature of time itself. Of course, skeptics argue we're still in early stages, but the implications are staggering. If time crystals truly tap into higher dimensions, they might be our first tangible window into the hidden architecture of the universe. With that in mind, let's venture into even stranger territory, theoretical spaces where dimensions don't just hide but flip into negative values. Now, let's take a sharp turn into one of the most counterintuitive ideas in physics: negative dimensions. If the thought of extra dimensions is mind-bending, wait until you hear about spaces where dimensions don't just extend beyond our perception, but flip into the negative. Negative dimensions sound like something out of abstract mathematics, but they might actually describe real phenomena in the universe. In simple terms, while we're used to dimensions being positive, like the three spatial dimensions we move through, negative dimensions represent a kind of inversion where the usual rules of geometry break down. Imagine a space where distances don't behave the way they should, or where shapes fold in on themselves in impossible ways. So where could these strange dimensions show up? One compelling idea ties them to topological defects, flaws in the fabric of spacetime itself. Think of the universe like a vast cosmic tapestry. If there are wrinkles or tears in that tapestry, they might be described by negative dimensional math. Some physicists speculate that these defects could explain anomalies in quantum fields or even dark energy's mysterious influence on cosmic expansion. Another wild possibility: negative dimensions might play a role in certain quantum phenomena like entanglement. If particles can somehow communicate instantaneously across vast distances, could their connection be routed through a negative dimensional space? It's a fringe idea, but it highlights how radically our understanding of reality might shift if these concepts hold water. Of course, negative dimensions remain highly speculative, and even mathematicians debate how to interpret them. But that's the beauty of theoretical physics. It pushes us to question not just what we know, but the very framework we use to describe reality. And if negative dimensions are real, they could rewrite the rules of the cosmos in ways we can't yet imagine. With that in mind, let's shift gears to another mind-stretching idea: the possibility that the universe itself might have a fractal nature, where dimensions aren't whole numbers at all. Now, let's unravel another layer of cosmic mystery: fractal dimensions. Picture the universe not as a smooth, neatly ordered space, but as an intricate, infinitely repeating pattern where dimensions themselves might not be whole numbers. This isn't science fiction, it's a serious theory that could bridge the gap between the tiny quantum world and the vast cosmos. Fractal dimensions challenge our everyday intuition. Normally, we think of dimensions as simple integers: 1 for a line, 2 for a plane, 3 for the space we live in. But fractals, those mesmerizing shapes that repeat at every scale like snowflakes or coastlines, defy this simplicity. They exist somewhere between dimensions with fractional values. For example, a crinkled surface might have a dimension of 2.5, not quite flat, not fully three-dimensional. So how could this apply to the universe? At the quantum level, spacetime might not be smooth but instead resemble a fractal, full of twists and folds at unimaginably small scales. This could explain why particles behave so strangely. Their reality might be governed by rules we can't see because we're stuck perceiving only whole dimensions. On the cosmic side, the large-scale structure of the universe, with its web-like distribution of galaxies, eerily mirrors fractal patterns. Could this be a clue that nature operates with fractional dimensions across all scales? The real magic lies in scale invariance, the idea that the universe looks similar no matter how far you zoom in or out. If spacetime has a fractal nature, it could unify quantum mechanics and general relativity by revealing a hidden symmetry between the smallest particles and the largest structures. Imagine a single mathematical framework describing everything from the behavior of quarks to the expansion of galaxies. Of course, this idea is still speculative, but it's a thrilling direction for physics. If fractal dimensions are real, they'd force us to rethink not just the fabric of reality, but how we measure and perceive it. And with that, we're ready to dive into another enigmatic possibility: the fleeting, flickering dimensions hidden in the quantum foam of empty space. Now, let's shift our gaze to the very fabric of empty space where nothingness might hide the most astonishing secrets. Quantum foam, a turbulent sea of energy at the tiniest scales, could be the stage for extra dimensions flickering in and out of existence. Picture spacetime not as a smooth, tranquil surface, but as a bubbling, frothing ocean where microscopic ripples might reveal hidden layers of reality. At the heart of this idea is vacuum energy, the notion that empty space isn't truly empty. Even in a perfect vacuum, particles and antiparticles constantly pop into existence, borrowing energy from nowhere before vanishing again. This zero-point energy, the lowest possible energy state of a quantum system, suggests that the void is alive with activity. But here's where it gets wild. Some theories propose these fleeting particles might be interacting with extra dimensions too small and unstable for us to detect. The Casimir effect offers a tantalizing clue. When two metal plates are placed incredibly close together in a vacuum, they're subtly pushed toward each other. Why? Because the space between them restricts the types of quantum fluctuations that can occur, creating an imbalance in vacuum energy. If extra dimensions exist, they could influence this effect in ways we're just beginning to explore. Imagine these hidden dimensions as tiny, curled-up loops that briefly unravel, altering the energy landscape of the quantum foam. What's even more mind-bending is the possibility that these dimensional fluctuations could explain dark energy, the mysterious force accelerating the universe's expansion. If energy from extra dimensions leaks into our own, it might be driving this cosmic acceleration, turning the vacuum itself into an engine of creation. While this remains speculative, experiments with ultra-sensitive instruments are probing these quantum whispers for signs of extra dimensions. Every flicker in the vacuum could be a message from a hidden layer of reality waiting to be decoded. And with that, we're ready to explore another cosmic puzzle: how the very number of dimensions we experience might have changed over the history of the universe. Now, let's journey back in time to an era when the universe itself might have been reshaping its very structure. Imagine a cosmos where the number of dimensions wasn't fixed but evolved, like a growing organism shedding old layers to make way for new ones. This is the heart of dimensional evolution theory, the idea that the dimensions we experience today might not have always existed in their current form. Think of the early universe as a boiling cauldron of energy, where space and time hadn't yet settled into the stable framework we know. Some theories suggest that in those first moments, extra dimensions were not just hidden but actively collapsing or expanding. As the universe cooled, certain dimensions could have frozen into their current compactified state, while others faded away entirely. This dramatic reshuffling might explain why our universe seems so finely tuned for life. If too many dimensions had remained accessible, gravity could have been too weak for galaxies to form, or atoms might never have stabilized. One compelling angle ties this idea to cosmic phase transitions like water turning to ice, but on a universe-sized scale. Just as water molecules rearrange when freezing, the fabric of spacetime might have undergone similar shifts, locking dimensions into their current configuration. These transitions could have released enormous energy, potentially even triggering events like inflation, the rapid expansion thought to have shaped the early cosmos. What's truly fascinating is how this theory bridges gaps in our understanding. If dimensions evolved, it could explain why we observe certain constants in nature, like the strength of gravity or the speed of light. They might not be fundamental truths, but artifacts of a dimensional selection process that favored stability. Some models even propose that other universes, with different numbers of dimensions, could have formed alongside ours, each following its own evolutionary path. While still speculative, this idea pushes us to rethink not just where dimensions are hiding, but when they might have changed. Future experiments probing the cosmic microwave background or gravitational waves could reveal echoes of these ancient dimensional shifts. And with that, we're stepping into our final theory, one that challenges whether dimensions are even the ultimate foundation of reality. Now, let's take one final leap into the unknown, where even dimensions themselves might not be the bedrock of reality. What if the very fabric of space and time, with all its hidden layers, is just a surface-level illusion? This is the radical proposition at the heart of our 30th theory, that dimensions could be emergent phenomena, bubbling up from something far more fundamental, a reality where dimensionality doesn't even exist. Picture a vast ocean. The waves we see on its surface, rising, crashing, interacting, aren't the ocean itself, just temporary patterns emerging from its depths. In the same way, our universe's three spatial dimensions and one of time might be fleeting ripples in a deeper, dimensionless reality. Some quantum gravity theories, like loop quantum gravity or causal dynamical triangulations, hint at this possibility. They suggest that at the tiniest scales, spacetime isn't smooth and continuous but granular, like pixels on a screen. Zoom in far enough and the concept of where or when might dissolve entirely. Even string theory, with its reliance on extra dimensions, has spawned ideas like matrix theory, where dimensions emerge from the interactions of zero-dimensional objects, points without any size or structure. It's as if the universe is a cosmic mirage, with dimensions materializing from something utterly alien to our experience. This perspective flips the script. Instead of asking how many dimensions are hidden, we might need to ask whether dimensions are real at all. The implications are staggering. If dimensions are emergent, then the laws of physics we take for granted, like causality or locality, could be approximate, valid only in our limited slice of reality. It might explain why quantum particles can seemingly defy space and time, or why black holes scramble information in ways that defy dimensional logic. Some researchers even speculate that a dimensionless foundation could unify quantum mechanics and gravity, not by adding layers to reality, but by stripping them away. Of course, this remains one of the most speculative ideas on our list, but that's what makes it thrilling. Future experiments probing the Planck scale or quantum entanglement might reveal cracks in our dimensional illusion. Until then, it invites us to wonder, are dimensions the stage of reality or just part of the play? With that, we've journeyed through 30 mind-bending theories, each a testament to how much we've yet to discover about the hidden architecture of existence. As we wrap up this cosmic journey through hidden dimensions, let's take a moment to reflect on the astonishing range of ideas we've explored. From the precise mathematics of string theory to the mind-bending possibilities of emergent dimensions, each theory offers a unique window into the unseen layers of reality. Some are grounded in rigorous physics, while others stretch the limits of imagination, but together, they reveal just how much we still have to uncover about the universe's deepest secrets. What's truly remarkable is how these theories don't just challenge our understanding of space and time, they redefine what it means to explore the unknown. Whether it's brains colliding in higher dimensions or reality itself as a holographic projection, these ideas remind us that the universe is far stranger and more wonderful than we often assume. And while some may remain speculative for now, history has shown that today's wildest ideas can become tomorrow's breakthroughs. So here's the big question. As technology advances and experiments probe deeper into the fabric of reality, which of these theories do you think will stand the test of time? Could hidden dimensions hold the key to unifying physics, or will we discover something even more unexpected? Drop your thoughts in the comments below. We'd love to hear which theories sparked your curiosity the most. If you enjoyed this dive into the mysteries of the cosmos, don't forget to like, subscribe, and hit the notification bell so you never miss an exploration of the universe's biggest questions. Thanks for joining us on this journey through the hidden dimensions, and who knows, the next great discovery might be just around the corner.